So when I was in graduate school, I actually had the opportunity to read Carl Pearson's original paper, and I was really impressed by the elegance of his mathematics. And this one idea really, in my opinion, was so beautiful. The idea was the distribution of scores when you use his procedure, assuming the null hypothesis is true, and we say under the null hypothesis as sort of a shorthand way of saying that. So what he showed was, under the null hypothesis, the distribution of scores using his metric where, we take the observed minus expected quantity squared divided by expected, we add up all those contributions, we get a chi-square score. That value, the distribution of that value under the null hypothesis only depends, it's amazing, on the number of rows in the table and the number of columns in the table. And this is called degrees of freedom. Degrees of freedom is sort of a sophisticated idea that comes from functional analysis. It's definitely not a statistics 1 idea, but I can show you how you could get this if you ever forget the formula. And this is a good description of what degrees of freedom is. But you take the number of rows in the table, subtract 1, the number of columns in the table, subtract 1, and multiply them, and you get this quantity called degrees of freedom. And the remarkable thing is that we call it a null distribution. So the distribution of the chi-square scores, assuming the null hypothesis is true, that is, assuming independence between the attributes, this chi-square distribution only depends on this, the degrees of freedom. And this was one of the fundamental ideas that when I studied statistics in graduate school, I was really impressed by. Not that it's true. I was impressed by the fact that a human being, through the use of mathematics, was able to elucidate the fact that this was true. So we talk about now, if you're really going to say this right, like if you're going to communicate with your professor and you really want to come across as knowing what you're doing, you really want to say the degrees of freedom of the null distribution. That's the language that you would say if you want to come off like, a statistician. The degrees of freedom under the null of the degrees of freedom of the null distribution. Now, it is sort of crazy that I get excited about this stuff. It brings back my passion for the subject. It is remarkable that Homo sapiens have discovered this. So here's a little example. Let's say we were going to perform a chi-square test of independence to see if class standing and the preference for multiple choice exams, which I know everybody prefers, are independent at a certain significance level using Pearson's chi-square test of independence. So you would need to know the degrees of freedom so that you could get the null distribution, which would then give you percentiles of the chi-square statistic that you could compare to. So what would the degrees of freedom? Well, first thing you need to do is count up the number of rows. 1, 2, 3, 4. See, it's freshman, sophomore, junior, and senior. Now, see where it says total over here? This is not a row. This is just put there for convenience, right? But the actual class standing categories are freshman, sophomore, junior, and senior. There are 4 of them. So there are 4 rows. Now, prefers multiple choice exams. We have yes, we have no, and we have no opinion. Total does not count as a column. That's just put there for convenience. So we have 3 columns, 4 rows, 3 columns. So 4 minus 1 is 3, 3 minus 1 is 2, 3 times 2 is 6. 6 degrees of freedom. So if you want to copy this down, feel free. Pause the video. And if you want to copy down this, feel free. Pause the video. Now, these percentiles that I've been alluding to but not clearly defining yet are going to be clearly defined. And now we call the percentiles that we use in hypothesis tests to be called critical values. And we say critical values of the null distribution. And it is kind of important to use the phrase null distribution because that really emphasizes to the reader or the listener or the viewer that we are assuming that the null hypothesis of independence is true. This whole chi-square business is based on an assumption, the assumption that the null hypothesis is true. And if this assumption is true, well, for the number of degrees of freedom that we have for the smallpox example, which, in fact, I should probably ask you to do that before we even look at this. If you look at the smallpox example, we have vaccinated, yes, no. That's 2 rows. And we have survived. I think it was died, yes, no. So that's 2 categories for the columns. So 2 minus 1 is 1. 2 minus 1 is 1. 1 times 1 is 1. So the smallpox example would have 1 degree of freedom. Now, the way the chi-square test works is we use, if the significance level is 5%, we use the 95th percentile as the critical value, as the cut point between a chi-square that's high and a chi-square that's low. So let me roll this idea by you. For the smallpox example, if we get a chi-square score anywhere between 0 and this critical value of 3.84, we call that a low chi-square. But as soon as we're equal to 3.84 or more, we call that a high chi-square. This critical value is the 95th percentile of the null distribution. 95th percentile. So here, this is where we're going to be rejecting the null hypothesis. If the chi-square score is greater than or equal to this critical value, we're going to reject the null hypothesis. And this critical value is the 95th percentile. Now, sometimes you might want to do a hypothesis test at a different level of significance, like, I don't know, for example, the 99th percentile. So then if we used the 99th percentile instead of the 95th percentile, we would actually be at the 1% level of significance. So this, if you remember this rule with these 2 points, you're going to be fine with chi-square. If the significance level is 5%, then the critical value is the 95th percentile of the null distribution. If the significance level is 1%, the critical value is the 99th percentile of the null distribution. I think you can see that 5 plus 95 equals 100, and 1 plus 99 equals 100, and percentile is that 100 idea. So here's sort of a general idea. In general, right, though, you know, alpha is equal to 5% and alpha is equal to 1% are the most common significance levels used in actual practice. In general, the 1 minus alpha quantity times 100th percentile is the critical value of the test, where alpha denotes the significance level. So the way you roll through one of these tests, right, is you need to know the significance level first, well, which by default is 5%. You need to know the degrees of freedom, which Carl Pearson showed was the number of row categories minus 1 times the number of column categories minus 1. You look up the percentile in a table, and that gives you the critical value. And there's a little symbol that some statisticians use for this critical value. And this is the symbol right here. It's a chi-square with two subscripts. Two subscripts, not one, two, separated by a comma. The degrees of freedom and the significance level. So let's return to the smallpox example. The value of Pearson's chi-square test statistic was observed to be 1,079.917. Now, since there are two row categories and two column categories, the null distribution of this test statistic has 2 minus 1, which is 1, times 2 minus 1, which is 1, and 1 times 1 is 1 degree of freedom. Accordingly, if we wish to test the hypothesis of independence at the 5% significance level, the critical value, separating a high chi-square from a low chi-square score, is the 95th percentile of the chi-square distribution with 1 degree of freedom. And here I've taken a little screenshot of part of the chi-square table. So if you take this 1 degree of freedom and you move it over to the 95th percentile, you'll see you get 3.8415. So make sure you see that 3.8415. I'm going to see if I can make this a little bigger for you viewers out there in internet land. Can I make this a little bigger? So can you guys see 1 degree of freedom, 95th percentile, 3.8415, and that is your critical value. So we have a test statistic of like over 1,000, which I told you was humongous. That means really, really, really large. And we have a critical value of 3.8415, which is the 95th percentile of the null distribution. And this chi-square score is way above that critical value. I mean, way above that critical value. I mean, this is probably one of the reasons why we use vaccines today, because the effect was so large. So, using that rule, we can reject the null hypothesis. And there are a few different ways of saying this in standard written English, and I want to read them all to you. The results suggest that vaccination and mortality are not independent at the 5% significance level. It's one way to write it. Here's another. The results suggest a statistical link between vaccination and mortality. It's another way to write it. Here's another way. The results provide compelling evidence that vaccination and mortality are not independent at the 5% significance level. That's another way to write it. Here's another. The results suggest there is a significant association between vaccination and mortality. That's the way I really like. I like that. Significant association. So let's do a multiple choice question where we put some of this to use. A market researcher wishes to test whether the new commercial works better than the old commercial at selling good smell underarm and body deodorant. The new slogan is, if you don't have time to bathe, just splash on some good smell. Tss. The old slogan was, good smell, the way to go when you're on the go. Tss. The statistician at the market research firm that you work for faxed you the results of her analysis. The problem is that all you can read is the following. The results of the statistical analysis is that the chi-square test statistic was observed to be 2.211 with 2 degrees of freedom, and the rest is cut off. And you have to be on that plane to California to give your PowerPoint, and you haven't even made the PowerPoint yet because you're going to make it on the plane on the way to California. You're freaking out. You took statistics with that great professor you told me about, your boss says. What does this mean? Don't share too much with your boss. Good advice. So let's roll through this step by step. So it says pick the best choice. Proposition 1, the results suggest failing to reject the null hypothesis at the 5% significance level. All right, so we know the chi-square score, that's 2.211, and we know the degrees of freedom, that's 2 degrees of freedom. So we have to look up, now see this says 5% significance level? Ask yourself, what percentile do I use? And if you said the 95th percentile, you'd be right. So you go to the table and you find the 95th percentile with 2 degrees of freedom. So when you go to the back of the book and you look up Appendix A statistical tables, you find selected percentiles of the chi-square distribution. So you go to 2 degrees of freedom and you go to the 95th percentile and you see it's 5.9915. So that's the critical value, 5.9915. So after looking this up in the table, we compare the chi-square score to the critical value. I'll just write crit, C-R-I-T, for the critical value. We compare the chi-square score to the critical value. The chi-square score was observed to be 2.211, but the critical value was 5.9915. So, since, I did something wrong. So since the chi-square score is not greater than or equal to the critical value, we fail to reject the null hypothesis. So let's go back to the question. So the results suggest failing to reject the null hypothesis at the 5% significance level. So that's true. So proposition 1 is true. Now let's look at proposition 2. The results suggest that the two slogans are associated with different sales rates. Now I want you to ask yourself this question. Which hypothesis, namely the null or the alternative hypothesis, which hypothesis corresponds to the phrase associated with different sales rates? Different sales rates.
Different sales rates.
So the null hypothesis would be that there's no difference between the sales rates. In other words, there's no link between which slogan you use and your sales rates. Right? There's no link, there's no connection, there's no association. They're independent. Right? So if we say associated with different sales rates,
associated with different sales rates,
that is the alternative hypothesis. So we can translate proposition 2 as saying the results suggest failing to reject the results suggest rejecting the null hypothesis, because the alternative hypothesis is different sales rates. Now, we have to fail to reject the null hypothesis at the 5% significance level. If you take a look at the chart, what you'll see is that the percentiles of the chi-square test increase as the significance level decreases. Now think about it, right? The 5% significance level is the 95th percentile. The 1% significance level is the 99th percentile. So this critical value is going to be even larger than this critical value. So without even looking at the table, you know that the 99th percentile of the chi-square distribution is even larger than the 95th. So that if you fail to reject at the 5% significance level, you must also fail to reject at the 1% significance level. So this would be true. Proposition 1 would be true but proposition 2 is false. The results suggest failing to reject the null hypothesis at both significance levels. So the answer to this multiple choice question is B. So now that we've experienced that question, here's another question that might be a good one to consider.
20. A statistician performs two chi-square tests of independence with the same number of degrees of freedom using Pearson's procedure. For the first hypothesis test, the significance level is 5%, and for the second, the significance level is 1%. The first hypothesis test has a greater critical value than the second. 2. The null hypothesis is true more often when we use the first hypothesis test.
So this is a relatively conceptually rich, somewhat difficult question, actually, but it really sort of bounces off the first question that I just did with you. So if you look at this, it says for the first hypothesis test, the significance level is 5%, and for the second, the significance level is 1%. So that means for the first hypothesis test, the percentile is 95th percentile. And for the second, the percentile is the 99th percentile. So it says the first hypothesis test has a greater critical value than the second. That's not true, because the first hypothesis test has a critical value that's the 95th percentile, which is not greater than the 99th percentile. All right, that's the first one. The second proposition is tricky, tricky, tricky. I would never give this to a student without first giving them this question first to think about. This is tricky. This says the null hypothesis is true more often when we use the first hypothesis test. Now this is tricky because the null hypothesis is either true or false, but we do not affect it by trying to study it, at least, not at the macro level. I'm not talking about quantum mechanics or any weird stuff here. I'm talking about standard statistics. The null hypothesis just says there's no link between this and that, probabilistically. That's what the null hypothesis says. This and that are independent attributes. That's what it says, right? The human being doesn't affect that by studying it. The human being is just trying to measure this, on the macro level, standard stats, So this would be false because, the null hypothesis, whether, we're just trying to study it, so we can't affect its truth. So this is false, and this is pretty tricky. And the way I phrased the answer is the null hypothesis is either true or false. What lies in the practitioner's realm is this should be is, not in. I'm going to fix this. Is not to determine whether the null hypothesis is true or false, because that is an impossible task, but whether to reject or fail to reject the null hypothesis. In other words, the statistical test cannot mirror absolute truth. Accordingly, proposition 2 is false, and the answer is D. This is kind of a tough one. I can't imagine most professors would give a question like this. So if you're looking at this for another course and this one sort of flew over your head like a bird, I don't know if I would stress too much about it, but if you're in my class, these are the sorts of things that I focus on. I want my students to understand that when a statistician performs a hypothesis test, we don't affect whether a hypothesis is true or false. We're just trying to measure it on the macro level. And so either the null hypothesis is true or the null hypothesis is false. But we, as humans, as Homo sapiens, have nothing to really do with that. All we can do is decide whether to fail to reject the null hypothesis or reject the null hypothesis. But that doesn't affect whether or not it is actually true or whether or not it is actually false. So there's a little bit of philosophy possibly in that idea. It's a little bit of a sophisticated idea, but it sort of falls in line with the difference between proof and evidence, the difference between a search for models and a search for absolute truth. Science does not search for absolute truth. We can't. But what science does search for is models that explain and predict that which we are capable of observing. And using models that are good models. You can have some really crappy models out there, you know. Not all models are good. Models have to be validated and tested for fit, really, in good science. You know, models aren't just accepted. They're tested. But what science really does is we search for models that explain and predict that which we can observe. And then we use these models to test hypotheses and make decisions. And sometimes we can come up with some really, really good models. And sometimes we come up with models that are pieces of crap.